All right, so today we're going to first start talking about something called gas stoichiometry. We did stoichiometry with grams and moles and molecules. Now we're going to move into gas. So the way that we can use this in gas stoichiometry is using our Avogadro's principle. Does anyone remember what Avogadro's principle was? That's Avogadro's number.
Oh, you're killing me.
What's the principle that goes with this chapter? Yeah, Jenna, what do you think?
Under equal conditions, temperature, pressure, equal volumes of gases contain equal numbers.
And what's the actual conversion factor for Avogadro's principle? Yeah, Alexis. That's the universal gas constant. Good. Close. 1 mole equals how many liters, Abby? 1 mole equals 22.4 liters. We're going to use this conversion factor to do gas stoichiometry. We know the conversion factor between grams and moles. We know the conversion factor between moles and molecules. Now we know the conversion factor between moles and the liters of gas, so moles and volume. Okay, so we're going to use this a lot in our conversion factors. Otherwise, we're going to solve the problem exactly the same way. We're going to solve our stoichiometry problems the same way using those T-charts. Okay, it's much less T-charts than stoichiometry. We don't have to do 4 per problem, right? This is just a one-stop kind of thing. Okay, all right, let's try this one. How many grams of Al2O3 are formed from 15 liters of O2 at STP? We're going to give you the balanced reaction here, but can someone name this molecule? Al2O3. Yeah, Trevor, what do you think?
Aluminum oxide.
Perfect. Aluminum oxide. Very good. Okay. And O2 is what?
Oxygen gas.
Oxygen gas. Good, right? If it's O2, that means it's a gas. Oxygen can't survive by itself on its own. Okay, it has to be O2. And here is your balanced reaction. All right, let's go ahead and start working here. We're starting to find out, we want to find out how many grams of aluminum oxide are formed from 15 liters of oxygen at STP. So in a T-chart, we always start with what? We always start with what we know, and we know we have 15 liters of O2. 15 liters of O2. This only works at STP, right? Because the 22.4 conversion factor only works at STP. So we have to make sure that our problems are at STP, okay? 15 liters of oxygen. If I want to get rid of liters, what do I have to go to? Moles, right? I have to go to moles. Moles always gets the 1. And how many liters are in every mole at STP?
22.4.
And does it matter what type of gas or what molecule we're using right here? The conversion factor is always the same at STP. Every single gas has 22.4 liters of equals 1 mole. Okay, every single gas. So we want to go from moles of O2. I want to get rid of moles of O2. What needs to go on the top? Good, moles of Al2O3, what we're going to. And these numbers come from where? Balanced equation. So it happens to be, happens to be 3 and 2. And then here we want to get rid of moles and go to grams. So we need to find the molar mass of that Al2O3. So molar mass, we need out our calculator. I think aluminum somewhere around 107.8, 107.9, something like that. Aluminum's what? 27, I'm sorry. 107 is silver, Ag. Jake, do you have the molar mass for me? Of Al2O3 or not quite yet?
Yeah. About 102.
About 102 grams, do we agree?
Yeah.
Okay. Now we multiply across the whole top, divide by the whole bottom. So 15 times 2 times 102, divided by 22.4, divided by 3. Bless you. Abby, what'd you have? 45.54 grams. Do we agree? Very good. That's what I had too. Let's try this next one. There's our balanced equation. We want to find out how many liters of water can be made from 6 grams of H2. Alright, so we're going to start with what we know, which is 6 grams of H2. We want to get rid of grams of H2 and go to moles of H2. How many grams are in a hydrogen gas molecule? 2 grams per 1 mole. Okay, the mole ratio here happens to be 2 to 2. You want to go from moles of H2O to liters of H2O. Here comes my conversion factor, so mole gets the 1 here. We know there's 22.4 liters in any mole of gas at STP. Brenna, what'd you have? That's okay. Perfect. And what's our units here? Liters of H2O. Very good. Do we agree? All right, great. Very good. All right, so now we're going to move into kind of the states of matter. And we're going to talk a little bit more about solids, liquids, gases. We're going to talk a little bit more about freezing and melting points. We're going to look at a phase diagram of water and to see how real gases act as compared to ideal gases. Okay, because all these things we've been doing so far have been for ideal gases. Not necessarily how they work in the real world, but pretty close. Okay, so we're going to examine real gases at the end of the day today. Okay, so this is chapter 10, section 4, but we're talking about changes of state, okay, states of matter, or we're talking about phase changes. So when I say it's in the gas phase or in the solid phase, that means any part of the system that has uniform composition and properties. So what we're saying is basically we're telling what state of matter it is at that point. Okay, it's in the gas phase. That means all of those molecules in that phase are uniform. I want you to turn to page 342 in your textbook and get that table put into your notes. Condensation is the act of a gas changing to a liquid. Okay, a gas changing states or changing phases to a liquid. Okay, when this happens, when this gas changes to liquid form, do you think that's the process of heating up, or do you think that's a process of cooling down? Cooling down, very good. Okay, gas particles have more energy than liquid particles. Liquid particles have more energy than solid particles. So as we lose that energy, we're starting to cool down. Where do we see condensation the most? Yeah, like on your drink, if you put it out in a little bit hotter weather and you have a cold drink. If you see it on glass windows, on your cars, all that kind of stuff, you'll see condensation. Okay. Gas, vapor turning to liquid. Yeah, pretty much. Yeah, that humidity in the air becomes, drops on the grass. Yeah, good. Okay. So that's cooling down. When we talk about states reaching an equilibrium, we're talking about each of those two things that are put in the same place reach the same temperature. Okay, so we have two opposing changes, and we get them to kind of equal a balance, right? One thing's really hot, one thing's really cold. Eventually, they reach an equilibrium point where there's no more change. The condensation that's happening within this vessel, it says some of these particles are starting to evaporate, and at the same time, some of them are starting to condense and become liquid again. So once it reaches that equilibrium point, we have a constant change of those two happening at the same time, basically. It's at the same rate. So if one evaporates, one condenses. If one evaporates, one condenses. It's at that equilibrium rate, okay? This is called equilibrium vapor pressure. So once it reaches that equilibrium and those gas particles have so much energy and they're starting to cool back down again, that causes what's called equilibrium vapor pressure. Okay, that's what we just talked about. Pressure exerted by vapor in a closed system. So this pressure can't happen if it's an open system, right? It's got to be a closed container. Otherwise, we don't have very much pressure. We want a closed container which we can read that pressure in. Okay. Vapor pressure is found mostly in what we consider volatile liquids. Okay, volatile means they're easily flammable, they're easily reactable, maybe not with water, but with other chemicals. But volatile liquids have weak intermolecular forces, so they break apart and they condense and evaporate very quickly, okay, very rapidly. An example of a volatile liquid would be alcohol. Okay, alcohol has a really low boiling point and a really low melting point, so it has weak intermolecular forces, and that alcohol evaporates a lot quicker than water does. Right, have you ever spilled rubbing alcohol on the counter and you notice that it's gone within a couple of seconds? Has that ever happened? Not really. Okay, if you spill water on the counter, it's going to sit there for a long time. If you spill rubbing alcohol on your counter, it's going to be gone almost instantaneously. It evaporates very quickly. Okay. So let's talk about actual boiling. It takes a liquid to a vapor within the liquid, sometimes below its surface. When you boil water, you notice that the bubbles come from the bottom, right? That vapor starts below the surface tension of the water. So vaporization at the boiling point occurs within the liquid, which is why the bubbles start at the bottom, and it happens at the top too. Okay, we see those bubbles make their way to the top of the liquid. Hopefully you all have boiled water before. You don't help your mom cook? Okay, the reason that this happens, the reason that we have boiling, right, is because we're adding energy in the form of heat. Okay, and that energy breaks down those liquid bonds so that it can release as a gas. The boiling point, we often just think of it as the temperature at which water boils or a liquid boils. What we're talking about for the boiling point is actually in which the equilibrium vapor pressure equals the atmospheric pressure. So we have kind of a closed container. If you're boiling water, it's pretty condensed, pretty closed, and it's a liquid, so it can't escape necessarily. Once it reaches that equilibrium point where you see vapor bubbles within the water and it's just on the brink of having a rapid boil, that's what we're talking about. That's its boiling point. Okay, we've got a few bubbles in there. It's about to break the surface of the water. That's boiling point right there. Okay, so you will see that equilibrium happen a little before you start having a rapid boil. It's when all those bubbles are inside the liquid, under the surface. Okay, so if you have lower atmospheric pressure, like if you're up in the mountains, you have a lower boiling point. Okay, a lower boiling point. Have you ever heard that? Like in Denver, things cook quicker. Okay, that's because you have a lower boiling point. It doesn't take as much heat. So lower the atmospheric pressure, lower the boiling point. Okay, so at its boiling point, which is usually just abbreviated BP, okay, all energy is used to evaporate the liquid or really vaporize the liquid to a gas state. Okay, the temperature remains constant as long as the pressure doesn't change. Normally the atmospheric pressure while you're cooking or while you're making things won't change, right? We don't have a drastic change in pressure in the atmosphere very often. So when we're at our boiling point, that liquid is constantly being heated at the same temperature, right? It remains a constant temperature until all of that liquid is evaporated. If you would let your pot of water boil all day, it would eventually all be gone, right? All of those gas particles would become, or all of those liquid particles would become gas and escape. Okay, freezing is the physical change from a liquid to a solid. Okay, almost all of our examples here are going to be given with water because that's the kind of most universal substance. It's the easiest to judge. We know a lot about water, so that's kind of our example for all of them. So freezing from a liquid to a solid removes energy from that substance. Okay, as we cool something down, we're removing energy. It's releasing energy. That's called an exothermic change. Exothermic means to release energy. Okay, so as a substance is cooling down, it's constantly releasing that energy back into the system or the atmosphere. Okay, sublimation is the state directly from a solid to a gas. Can anyone think of an example in real life that would happen? I can't think of any real examples. Your book might give a couple, I guess, but yeah, what do you think?
Dry ice.
Yeah, dry ice, that's a good example. Okay, we go right from a solid to a gas. More of a vapor state, but yeah, okay. All right. Deposition is changing of state directly from a gas to a solid. Okay, this one we hopefully you can think of an example of. Okay, because I have one in my head. Directly from a gas to a solid, what do you think? Or from a vapor to a solid? What do you think, Grant?
The formation of like hailstones and snow.
Okay, like precipitation out of the sky? Okay. What do you think, Payne? I thought you had your hand up. Not quite. Okay. Anybody else have an idea? Okay, what about the frost that you see on your windshield in the morning when it's cold? Do you see liquid drops of ice, like little droplets of ice, or do you see kind of a sheet that's spread out over your car? A sheet, right? That means those vapor particles stuck to your car and then froze almost instantaneously. Because if it would have had time to really liquefy, you would have seen little droplets of ice on your car, and that really doesn't happen, right? We see a nice even sheet. So it didn't really reach a liquid form. It just went pretty much from that vapor in the air to freezing on your car. Okay? That's why we see those crystals on there. All right, now we're going to start with a phase diagram. This is kind of our last little section here. Phase diagrams. Phase diagrams show us the relationship in real gases. Real gases. Okay, and it's a pressure versus temperature graph. Diagram. Okay, so this is the phase diagram of water specifically. Okay, and we're going to talk first about the triple point. So everybody find the triple point on your handout. Okay, it's right in the middle connecting those three curves. So triple point is actually a condition in which water can be a solid, a liquid, and a vapor all at the same time. So you can put this part in your notes if you want, or you can label it on your handout. That's up to you. Okay, but you need to understand what each of these parts mean, because I'm going to be asking you about that maybe on your test. Okay, so we need to understand what the triple point is and where to locate it. So it can go in your notes or it can go on the handout. That's fine. The triple point is pressure and temperature conditions that the water or the substance of any substance can be solid, liquid, and vapor at the same time. We can use the word vapor and gas pretty interchangeably. I'm going to explain the difference here at the end today. Okay. But let's take a look at the conditions. Is that pressure higher or lower than regular atmospheric pressure? What's regular atmospheric pressure? 1 atmosphere. So this is lower than regular atmospheric pressure. Okay, way lower. So it's really, really low pressure. The temperature at the triple point is 273.2. Is that above freezing point or below freezing point of water?
Above freezing.
Just slightly above. Okay, it's barely above. So that's why we can have them exist at all three states, right? It's just above the freezing point, so that solid is still going to stay, the liquid is going to stay, and the gas is going to stay. It's really rare conditions because that's really low pressure. Really low pressure. Okay? So that's the triple point. You need to know what it is and where it's located. The critical point is point E, so that's way up here on top. Okay, point E. And what the critical point tells us is that the substance no longer can exist in a gaseous state. Okay, so it can no longer be a gas because the temperature is too high and the pressure is too high. Right? It's starting to just condense smaller and smaller, and we just can't survive as a gas anymore. Okay? And for water, the critical temperature conditions are 647 Kelvin and 218 atmospheres. Okay, that's why those dotted lines are drawn there, because it's telling us exactly what those conditions are. Okay, so if I ever ask you for the critical temperature on this phase diagram, you should find where that critical point is and read the temperature that's corresponded with that. Okay, so if I give you a quiz or a test over this, you might get a different substances phase diagram. You should be able to read carbon dioxide phase diagram fine. Right? You should be able to read nitrogen gases phase diagram fine, because they're all formatted basically the same. Okay? Yeah?
Always temperature and pressure.
It should always be temperature on the bottom, pressure on the top. If it's not, for some reason, you have to look at it, but it's almost always. Okay? After it reaches that point, after it reaches its critical point, it forms something called a supercritical fluid. Okay? Supercritical fluid means it's basically like kind of half liquid, half gas, but it's mostly in that liquid form. It's reaching that fluid state. So it's no longer a gas. It reaches what's called a supercritical fluid. Okay, now we're going to talk about the curves that are on the graphs. We have curves A, B, and C. Yeah, I'm sorry. Yeah. Okay, so if I ask you what's an equilibrium on curve A, you need to tell me it's a solid and a gas, both. Okay? We need to understand what's happening with those curves. So if I ask you what curve B means, what do you think that's going to be in equilibrium between?
Solid and liquid.
Very good. It's in between solid and liquid. Okay, so anytime the temperature and the pressure meet somewhere on this point, on this line right here, I'm sorry, on this line, we're going to be in that equilibrium between solid and liquid. And we see this pretty often. Realistically, we see it pretty often. If we're looking at atmospheric pressure here, which is the normal atmospheric pressure for us just living in this world, okay, and we look at about freezing, that's right on that line. So right at our freezing point, 273 Kelvin is 0 Celsius, or 32 degrees Fahrenheit. 273 is our freezing point at 1 atmosphere. Isn't it on that line right there? Okay, so when we put a glass, or we put ice chunks in a glass of ice water, and those ice chunks start to melt, the temperature of the water comes up a little bit. It might reach that 273 Kelvin or the freezing point, but it doesn't freeze. But there's still some ice in the cup. Okay, so that's where we reach that equilibrium. If we still have some solid and we still have some liquid, but our temperature is at the freezing point. Okay, that's when that happens. And it really does occur pretty often. We just might not know it. So our final thing here, we're looking at the equilibrium curve between the gas and the liquid state. Okay, so here we get a little bit higher pressures, a little bit higher temperatures we're getting up here. We still have atmospheric pressure and 100 degrees Celsius. Right, that's kind of our boiling point right there. Okay, so 373 and 1 atmosphere, that's our boiling point. That's where we are at our equilibrium between liquid and gas. Okay, so those are pointed out on the graph to you with those dotted lines. Does that make sense? So if you want to put in right here, oops, I'm sorry. If you want to put right here, that's our boiling point, and here would be our freezing point. You know, that's what we're looking at here, our equilibriums. We're somewhere between boiling right here, and then we're somewhere between freezing right here on that line.